Welcome to the lesson on geothermal energy. In this lesson, we will provide you with an overview of geothermal energy, including its origins, applications, environmental impacts, and future potential. Let us look at our lesson objectives. By the end of this lesson, you will be able to list the advantages of geothermal energy. Next, you will be able to identify the challenges associated with using geothermal energy. Then, you will be able to describe the challenges and environmental hazards related to the geothermal energy. Finally, you will be able to explain how geothermal energy influences BEV manufacturing. What is geothermal energy? Geothermal energy is the heat generated and stored underground in the earth. It is a renewable source of energy that can be used to generate electricity, heat water, and power homes and businesses. Geothermal energy comes from the radioactive decay of materials in the Earth's core and the heat left over from the planet's formation. This heat is stored in rocks and fluids in the Earth's crust. Geothermal energy has been used for thousands of years for heating and bathing. The earliest known use of geothermal energy was in China, where people used hot springs to heat their homes and temples. The first geothermal electrical production plant was built in Italy in 1904. However, geothermal energy did not become a significant source of electricity until the late 20th century. Geothermal energy has been used for electricity generation and other applications in regions with geothermal resources, such as Iceland, New Zealand, and the US, since the mid-20th century. Geothermal energy offers significant benefits in power generation. Between 2010 and 2020, the cost of generating electricity from geothermal projects was relatively affordable. In countries like Iceland, El Salvador, New Zealand, Kenya, and the Philippines rely heavily on geothermal energy, with Iceland using it to cover more than 90% of its heating requirements. In these countries, geothermal energy plays a crucial role in meeting electricity and heating needs. In industrial applications, geothermal energy is especially valuable for steam generation. Steam is critical in many manufacturing processes, including sterilization, drying, and chemical reactions. Geothermal resources can produce high-pressure steam used in diverse industries such as textile processing, paper manufacturing, and pharmaceutical production. This makes it a versatile and efficient energy source for various industrial needs. One of the most striking features of geothermal energy is its minimal land footprint. Unlike wind and solar installations that require vast areas, geothermal power plants are compact. Most of the infrastructure, including heat exchangers, is underground, leaving very little visible above ground. In residential settings, heat pumps are about the size of a typical household appliance. Even in larger plants, the infrastructure is relatively small, with cooling towers and turbines being the most significant visible components. While some geothermal plants may have a visual impact on the landscape, newer architectural designs are working to minimize this effect, making the technology increasingly environmentally friendly and visually pleasing. Geothermal power plants are remarkably quiet during operation. While construction activities can generate noise, once the plant is operational, noise levels are minimal and hardly noticeable. This applies to both small-scale domestic systems and larger power stations with multiple turbines. Geothermal energy offers a consistent and reliable energy source. Unlike solar, hydro, or wind power, which are dependent on weather conditions, geothermal power plants can operate at full capacity 24/7, maximizing energy output. This continuous operation leads to higher energy production for a given nominal power capacity. Geothermal energy promotes resource efficiency. Not only can components of geothermal plants be salvaged and reused at the end of their life cycle, but the energy systems are designed to optimize heat utilization. Excess heat that cannot be immediately used is returned to the system, increasing overall efficiency. Geothermal power plants, both large-scale and domestic, are known for their exceptional longevity. They can last up to 80 or 100 years, significantly outperforming traditional heating systems like boilers, which typically last around 15 years. As there's no fuel involved, the risk of fire is eliminated, and the proven technology ensures reliable operation. Geothermal systems require minimal maintenance, especially in domestic settings. They work like a closed loop, automatically regulating the pressure of the fluid inside. The limited number of electrical and mechanical components further reduces the need for maintenance. While often associated with heating, geothermal energy is equally effective for cooling. Geothermal systems can be installed in various buildings, from homes to commercial spaces, providing both heating and cooling solutions. The only limitation is the specific geological conditions of the area. Geothermal energy can only be harnessed where hydrothermal resources exist, which are mainly found in the western United States. However, many of these sites lack access to the transmission lines needed to transport electricity. Additionally, drilling for geothermal reservoirs comes with uncertainty, as it can be challenging to successfully tap into the underground resources. Developing geothermal systems, particularly enhanced geothermal systems, abbreviated as EGS, can increase the risk of earthquakes. For example, in 2017, an enhanced geothermal systems project in South Korea triggered a 5.5 magnitude earthquake. However, in the U.S., strict regulatory standards and seismicity management protocols have minimized earthquake risks. As a result, earthquakes linked to geothermal development have historically not been a significant issue. Geothermal energy systems are expensive to develop, with capital costs exceeding $2,500 per kilowatt for larger facilities. In contrast, natural gas plants cost around $1,000 per kilowatt, and solar and wind energy projects range from $1,200 to $1,700 per kilowatt. Solar and wind energy have also benefited from more financial incentives and lower risks for developers. Despite the high initial costs, geothermal systems are sustainable and require minimal maintenance, making them a long-term energy solution. Geothermal energy can release harmful substances like hydrogen sulfide, ammonia, methane, and carbon dioxide into the air, and dissolved solids like sulfur, chlorides, silica, arsenic, and heavy metals into water systems, potentially harming wildlife. Many geothermal power plants require significant amounts of water for cooling, which can lead to conflicts in areas with limited water supplies or competing needs, such as fish spawning habitats. Geothermal power plant can sometimes cause the ground to sink or collapse, a process known as land subsidence. This happens when large amounts of water or steam are extracted from underground reservoirs, causing the surrounding land to settle unevenly. Additionally, geothermal systems often produce hazardous byproducts, such as toxic chemicals and heavy metals, which need to be disposed of safely. Improper handling or disposal of this waste could lead to long-lasting harm to the environment, including contamination of soil and water resources. The future potential of geothermal energy is promising due to its cost-effectiveness and reliability as a renewable energy source. According to the Annual Energy Outlook 2020, the levelized cost of electricity, abbreviated as LCOE, for geothermal energy is projected to be approximately $37.47 per megawatt hour by 2025. This competitive pricing positions geothermal energy as an attractive option compared to other renewables, making it a valuable contributor to sustainable energy portfolios in the coming years. Research and pilot projects are showing progress in developing enhanced geothermal systems technologies. These advancements could allow geothermal energy to be harnessed in areas without natural hydrothermal resources, potentially making geothermal accessible across the globe. As smart grid technology evolves, geothermal energy's stable output can play a key role in supporting modern energy systems, particularly in balancing intermittent renewables like wind and solar. Let's look at how geothermal energy influences BEV manufacturing. Geothermal energy can power BEV manufacturing plants with clean, renewable electricity, reducing pollution and carbon emissions. Using geothermal energy can lower electricity bills for factories, helping to reduce the overall cost of making BEVs. Some geothermal plants produce lithium from underground brines, which is an important material used in BEV batteries. This helps make battery production more eco-friendly. Let us now look at our lesson summary on geothermal energy. Geothermal energy uses heat from deep inside the earth to produce power. It does not take up much space, runs quietly, provides steady energy, and can be used for both heating and cooling. However, it has some challenges, such as high startup costs, limited locations where it works well, the risk of land sinking, water use problems, and possible air or water pollution. As technology gets better and costs come down, geothermal energy will become an important source of clean energy. It can also help power BEV factories and provide materials for batteries, making electric car production cleaner and more affordable. Thank you.